This is the working circuit. On one part of the FPGA, we are generating numbers. We are then sending it to the other part of the FPGA over a serial link. So we have a parallel to serial converter, then a serial to parallel converter, and then we're displaying the numbers. We have got the numbers changing at an offset. So you see first one number changes, then another, then the next one, it ripples through. So it shows you that everything's working. And each digit, if you look at it, you see that it is a +3 modulo 10 counter, and each one is just offset. And so each digit should change once a second, and they're nicely offset to get the effect that you're seeing here. So let's now jump and have a look at the actual project file to see what's happening in there. If you want to look through the files yourself, then you can open Project, go to where you downloaded the archive file to, and select the Quartus archive file. You can choose the destination folder name here. So that looks good to me. Click OK. And then it should import it for you. Looks like it's ready. If you have a board available, you can program it to the board. You can compile it, etc. We're just going to have a look at some of the files. So open up the file and start with the main module, which is stream numbers. In fact, before we look at this, let's look at the RTL view. We will need to compile it first though to do that. So compile. And we have finished compiling. So now when we go to the netlist viewers to look at the RTL view and maximize it, and we see our design here. So we've got our 50 megahertz clock coming in. We're generating 6 numbers here. So inside each one is our number generation unit, and we get out a 4-bit number, and the 4-bit number will be between 0 to 9 because that's how we've designed our number generator. These 6 different numbers all come out and they get combined into a 24-bit number that we put into our parallel to serial converter. Connecting our parallel to serial converter to our serial to parallel converter are just 2 wires. We've got our data wire here, out to in, and we have what I've been calling the live wire. So remember, if the live wire is 1, that means data is actively coming out of out and going into in here when the live wire is high. When the live wire is low, no data is being transmitted, and so the serial to parallel just needs to remember the previous number that it received. Of course, we're using a common clock in our design. I've been mentioning that for simplicity. If we don't have a common clock, things get a lot harder, a lot more quickly. But with a shared clock, this serial to parallel and back again is relatively straightforward. Once we've received our data, so if these chips are doing their job, then whatever number comes in here should, recenter this. If these chips are working properly, then whatever number is coming in here should end up out here. So this should essentially be a transparent link if we're doing a good job. And then, so we generate a number, we send it serially over here and recreate our number. And we split this 24-bit number, we split up into 6 binary coded decimal digits, and each one goes to a 7-segment decoder and gets displayed on the 7-segment displays. So whatever number this is generating should appear over here, whatever number this is generating should appear on this display, and so forth. The only other thing to consider is when should we do our parallel to serial conversion, and so I've added an extra pulse generator here to the start pin. So this pulse generator at regular intervals In fact, I have it set up for every millisecond. Every millisecond we'll get a blip coming out here, and that starting blip will cause the parallel to serial converter to do its job. It will take a snapshot of the input and then send it out bit by bit, one bit at a time, while asserting the live wire. The serial to parallel detects that the live wire is active, and every time it receives a new bit, it puts it into its shift register. So after it's received 24 bits, then the shift register in here contains the number that was being sent, and then it gets displayed there. Of course, if you want, you can hop into any of these by pressing the plus button here and seeing the circuit inside it. So how does the pulse generator work? Well, we have a counter here. I have made it a count down timer. Why do I make them count down timers? Because have a look, it's very easy to detect when the counter has reached 0. If I have to count up, then that means I have to detect when the output's equal to some particular number. I prefer to have it detecting when it's 0 because it's just nice and simple. You just put everything into an OR gate and then invert it, and then you know whether you've finished or not. That's just personal preference. Because it's a countdown timer, counter, timer, whatever you want, then we have to initialize it with the largest value when we want to start it. And so that's what this one does. This one says that if we finished our count, if we've gone down to 0, then we need to reset the count, and this is what we're going to set the count to. And this is chosen so that we get one pulse out here every millisecond based on a 50 megahertz clock. And if it's not time to reset the counter to its largest value, then of course the next count is just the previous count minus 1. And this circuit here somehow represents minus 1. Jumping now to our top level module, we see we have stream numbers here, and this is module stream numbers, so it's my top level module. I've got the 50 megahertz clock coming in, and the output are my 7 segment displays here. How do we know this is 50 megahertz? Because if we open and now we need to change this to, I'll just change it to everything to make it easier. If we look for our SDC file and open that, then we see we've created a clock with a period of 20 nanoseconds, and it's attached to the clock 50 pin. So now, due to the presence of this file, Quartus knows that clock 50 is indeed a 50 megahertz clock. So Quartus knows there's a 50 megahertz clock coming in here, and our outputs are our 7 segment displays. First thing I do is I generate my 6 different number generators. I want each number to increment every 1 second. With a 50 megahertz clock, that means I want it to increment every 50 million clock periods. And I also want my numbers to increment offset from each other. So because there are 6 counters, I divide the total period by 6, and I'm going to offset each count by an integer multiple of this offset, so that the digits won't change at once, the digits will change one after the other. That helps us verify that our design is indeed working correctly. The 6 numbers are going to be stored in 24 wires that I call number, and by grouping them together, that makes it easy for me to feed into the parallel to serial converter, etc. Verilog is a bit annoying. If you upgrade to system Verilog, I could have used a packed array here and it would have been a lot nicer. I could have told it I wanted to have 6 numbers. Each of the numbers will be 4 bits. But plain old Verilog doesn't allow you to do that in a convenient way. You can have arrays, but you can't do what I want to do with them in this program. Instead of writing out 6 number generators here, so remember each of these is going to be a physical chip, so to speak, I could have just instantiated 6 of them and 6 isn't too bad. But if I had 600, I would not be doing it by hand. So I showed you here how to use a generate block to allow you to generate more than one of the same thing. And it's better than more than one of the same thing. We can make slight variations to each one, which is what we need. When we have a generate block, we're probably going to have a for loop in there, and then the index needs to be of type genvar. You can't have an integer here. It needs to be of type genvar because it's special. So just remember this structure. It'll be create an integer, but not integer GI of type genvar GI. It will be an integer, but being a genvar, it's special. And then you have generate and nGenerate, and then your for statement here. You have to name your block. So you see I've given this block the name numgen, and that's because if I create 6 number generators of name ng, they'll all have the same name, and that's not acceptable. But by naming my block, then what happens is the name of each chip is going to be numgen 0, 1, 2, 3, 4, 5, 6 .ng. So by naming the block, I end up with a unique name for each of these chips I'm making. So if you like, every chip has got the same surname, ng, but its first name is numgen 0 or numgen 1 or numgen 2, etc., where you add the generated variable to the end of this name. And that's why you need a genvar up here, because it's special, it gets added to names. My number generator. So I'm now using a concept of a parameter that allows us to pass at the design phase, at the initial stage of the discovery phase. You can pass constants to modules. So rather than having to have a parallel to serial converter, which is of a fixed width, like 4 bits or 8 bits, I can specify the number of bits when I create that chip by passing to it a parameter. Here we're doing the same thing with my number generator. When we look at the number generator module later, we'll see that it has defined 3 different parameters, and I can give them values. These are not values that are passed in on wires in the FPGA. This is beforehand at compile time, so they're going to be fixed for the design. They're going to be fixed once it's designed. So the initial value of all my counters is going to be 0. So when we first run our code on the board, all 6, 7 segment displays are going to display 0. But when they change, is going to be different because they each have a different offset. And the offset is depending on their number. So GI is either 0, 1, 2, 3, 4, or 5 multiplied by, and the offset is the number of clock periods, and it's designed to be the total period divided by 6. So that nicely staggers each of the displays. One display will change, then the next, then the next, then the next. And the total period is 50 million clock cycles. That means that the number generator will generate a new number every 50 million clock cycles, i.e. every 1 second. And then this part here is where we actually wire up our chip. So we pass to it our clock. And over here, the output is going to be stored into number, but we're not going to store it into all of my number. The first number generator is going to be stored into bits 3 to 0 of number. The next number generator chip is going to use the bits 7 to 4 and so forth. And so I can specify the bit slice I want. I could have done GI times 4 plus 3 colon GI times 4. That would have worked. But it's even nicer to use this plus symbol here. And so GI times 4 is where I start. And plus 4 means I start there and include that bit and the next 3 bits. So this will give me the same thing as GI times 4 plus 3 colon GI times 4. It's the same thing here. Okay, so that's where I've connected all my wires. And if we hop back to the RTL view and we look at our number generator, you see that indeed is what's happening. Each output is 3 bits, but they somehow get aggregated all together into different fields here. So if I look at the connectivity details, it might help. And so here we see the number generator number 5 is going into bits 23 to 20, whereas the number generator number 0 is going into bits 3 to 0. So it's a very convenient way of grouping the outputs of all these guys into different bits in the same cable, so to speak. Okay, so that's our number generation code up here. The next thing we have is we're going to go from parallel to serial. And so for that, I've got my parallel to serial chip here. I configure it with a width of 24. I pass to it my clock. I need to work out how to tell it when to start doing the conversion. We'll come back to that in a second. Its output is going to be live and data, these 2 wires here. That's our serial connection. And what it's going to convert is the number. So we've generated a number and stored it on these wires here, and that's what the parallel to serial number is going to convert when we tell it to start. How do we tell it to start? Well, that's where I make use of another pulse generator. So I set my pulse generator to have a period of 50,000 clock cycles, which for a 50 megahertz clock means once every millisecond. So once every millisecond, start is going to go high for one period of the clock. And therefore my parallel to serial, it's going to be asked to do the conversion once every millisecond due to this code here. If we go to the RTL view, then we see there's our pulse generator that we looked at before, and it feeds into the start pin of the parallel to serial chip, telling it when to start the conversion once every millisecond as we have it configured now. At the receiving end, we have our serial to parallel converter here. It's also configured to have a width of 24 bits. It takes a clock, it takes our 2 data wires, live and data, and it outputs the number it received. And if everything works, then the number we generated up here and stored on the wire called numbers should come out here into RX. Jumping to the RTL quickly to remind you, these are the 2 wires, out and live, that transfer the data serially between the parallel to serial and serial to parallel. Finally, we just need to display the received number so I can verify that this works. There's a little trick here that I've done because I want to use another generate statement. Unfortunately, the pin definition file that comes with the board and that we just used to save ourselves time by not having to do the pin assignments ourselves, it declares hex 0 to hex 5 as individual variables. The technical name is nets, individual nets. Because I want to use a for loop to automatically connect up 6 converters to each one, then I need to put these guys into a single wire. And so here's my single wire. It's going to hold 42 bits, and so therefore it can hold all of these 6 7-bit wires here. And all I've done is I've assigned to them the value of hex. So this means that rather than me having to write down BCD to 7 segment, rather than me having to instantiate this 6 times, and each time passing to it hex 0, hex 1, hex 2, hex 3, hex 4, hex 5 by hand, I can now use this algorithmic method to achieve the same thing. So in more detail, if GI is equal to 0, then this will be 0 plus an additional 7 bits. Well, sorry, it'll be 0 and 7 bits in total. So that will be hex 6 down to 0. So it's going to be the first 6 bits of hex. But if we have a look over here, the first 6 bits of hex is going to be hex 0. So when GI is 0, this corresponds to the lowest 7 bits of hex, which corresponds precisely to hex 0. When GI is equal to 1, this will start at bit 7, and in total it will include 7 bits in the upwards direction. And so when GI is 1, this will be exactly the same as had I typed hex 1, and so forth. When GI is equal to 5, then this term here is equivalent to just hex 5 here, using this trick. And now I just have a second generate block. I can reuse the generate variable from up here, and I need 7 BCD to 7 segment converters, and so I just initialize each one. Sorry, I instantiate each one. Remember, I have to name my block here so that each of these guys will be called sseg0.bcd, sseg1.bcd, etc. The input, I pass to it part of the received number. And remember, when I was generating my number, I stored the number using part of number. My number and my RX are both 24 bits wide, but we want to group them into blocks of 4 bits. Every 4 bits stores our binary coded decimal. So we get 1 digit here and send it to one 7-segment display. Get the next digit, send it to the next 7-segment display, etc. And if we hop over to our RTL view over here, then we see that's exactly what's happening. The output here is 24 bits, but it gets broken up. Bits 3 to 0 go in here, bits 7 to 4 go in here, bits 11 to 8 go in here, 15 to 12 in here, 19 to 16 here, and 23 to 2 in here. And that's exactly what that code was doing there. Okay, let's have a look at the remaining parts of this code. Open our next file, and which one shall we look at? We'll look at the number generator next, going left to right in our block diagram, so to speak. Let's start at the bottom with the counter here. So the only change from the lecture notes is that I now have a parameter value here. So I'm able to, if I so wish, initialize my counter to start at whatever value I like. The inputs are the same as before. I initialize my count to the initial value. Now, to stop compiler warnings, and that's a good thing because compiler warnings normally tell you there's something wrong in your code, this parameter is going to be most likely a 32-bit integer. If I assign it to count, well, count is only 4 bits, I'm going to get a warning that Quartus has had to truncate a 32-bit number into a 4-bit number. So to let Quartus know that I'm aware that that's happening and it's not a problem, I explicitly say, well, I just want the lowest 4 bits of initial value. So that's just to stop the compiler warning, letting it know the truncation it will implicitly do is what I'm authorizing it to do. I'm happy for it to do that. And then the rest is the same as in the lecture notes. So this part should be okay. If we look at the pulse generator now, then I've given it both an offset parameter and a period parameter. Remember, I'm going to have a clock that basically counts from 0 up to the period -1. Or in our case, it's going to count down from period -1 to 0. So I need to be able to store the number period -1. So if my period is 50 million, I need to have a count register that has enough bits to store 50 million minus 1. And the nice way of doing that is to use this ceiling log2 function. So hopefully you know about log2. Because we're storing things in bits, then we use 2 to the power of n to know what we can store in n bits. So an n-bit number can store numbers from 0 to 2 to the power of n minus 1. So by using log2, we basically invert that operation. And C says ceiling, it says round up. Not round off, but round up. So this will tell us how many bits we need to store, technically not period, but period minus 1. But I only need to store period minus 1, so that's just perfect. So now I know how many bits I need for my count. I need n bits, and so it's going to be declared as n minus 1 to 0 to give me my n bits. So count is my state, next count is going to be my next state, and I initialize my count to the offset that we passed in. By default it will be 0, but I can start my pulse generator at an offset, so the first pulse I can make occur sooner if I wanted to by using this offset here. Again, to keep the compiler happy, I tell it that I'm aware that offset needs to be truncated to n bits, so please don't warn me about doing that. Then it's very similar to the lecture notes. We've always have got our flip-flops for saving the state and our next state logic. The only difference here is that I'm counting down, and if I get to 0, and I'll explain this in a second, then I'm going to go to period minus 1. And I tell it that I'm aware that period needs to be truncated to n bits. I've calculated n so that period will fit in it, but Quartus is not smart enough to know that, so I explicitly tell it that I'm very much aware it just needs to truncate period to n bits to fit into next count. If I haven't reached 0, then I just subtract 1 from the count. Now here I could have written count equals 0, but I was being a little bit smart, and what I did was I reused the output logic. So my output is going to be true if count is 0, and it's going to be false otherwise. Just like in C, if you convert a number to a logic expression, 0 is false and any other number is true. So if I take a Boolean not of this, I'm not using tilde because that would invert every bit and I don't want that. I want this Boolean operator, and this says that if count is true, and count is true if it's non-zero, then I'm going to get not true, which is false. So the whole expression will be false if count is not 0, and therefore the whole expression will be true if count is 0. So we output a pulse if count's 0. And because out is the same thing as testing whether count's equal to 0, I can reuse it here. Clearly this is not C code, this appears after that, but it's hardware, so it doesn't matter. That value is going to be the correct value to use no matter where this assign statement is. Finally, to generate my actual number, I just need to put together my pulse generator and my counter. And the only annoying thing is we have to pass through the parameters. So for my number generator, I now have 3 parameters. I've got the initial value for the counter, I've got the offset for my pulse generator, and I've got the period for my pulse generator. And I just have to pass these parameters to each of the modules when I instantiate them. And otherwise it's the same as in the lectures. If we want to go quickly back here, then you see how we use that. I'm going to initialize them all to 0. In fact, I don't even have to have this in here because the default was 0, but just in case you wanted to change it, you can. each of them is going to have a different offset, but they're all going to have the same period. So they're all going to increment once a second, but when they do it within that second is going to be different due to the offset. And that's achieved by having an offset into my pulse generator code. Okay, what's the next thing to look at? We want to look at our parallel to serial conversion. Our serial to parallel is very close to what's in the lecture notes. I just now have a parameter width, so I can vary the width of it. Therefore, when I declare my output out, it's going to be of size width -1 to 0. And similarly, when I have my shift register here, I need to use the width parameter to work out what I want here. The parallel to serial, in the lecture notes, I did it using a finite state machine because that way will always work, and it was good practice to do it that way. Here, I've done it differently to give you more practice. This time I've done it using, well, we'll go through the technique to see what we've done. But basically, we're doing it using a shift register as well. We have a parameter width, same as before. The start tells us when we want to start our conversion. When we start the conversion, we're actually going to store the input. The input is a parallel number of width bits, and the parallel to serial converter has got two wires coming out, live and out, which connect to the serial to parallel converter as we saw in the RTL viewer. We are going to, so how are we going to do this? Well, we're going to use a shift register. We're going to store our input into a shift register. And then every time we want to send a bit, we send a bit, then we shift our shift register along to get the next bit, as we'll see. So we're going to need a counter so we can count how many bits we have left to send. So when count is equal to 0, that means we're idle, we're not doing anything. Otherwise, count will tell us how many bits there are left to send. So in particular, count has to be able to store the largest number of bits that I might want to send. Well, I need to be able to send width bits, so I need to be able to store the number width, and so I need to do width +1 here when I do this C-log2 trick. So by declaring n this way, if count is n bits, then it's able to store width. It's big enough to store the number width, and that's what I need. So if we're going to be having a 24-bit parallel to serial converter, I need to be able to store the number 24 into count, and this here ensures me that I can do that. Here are our flip-flops, same as always. We just, for each state register, we declare another register for the next value it's going to take, and our flip-flop code simply assigns the next value to the current value. So always use this same format here. Then I just need my next state logic and my output logic. So my next state logic is combinational. There's a star here. The default is to do nothing. Remember, whenever you are declaring combinational logic, you must make sure to assign something to the outputs. Anything that's coming out has to have a value at all times. So the easiest way to do that is to put the default action at the start. Because it's inside a begin-end loop, then we're doing behavioral Verilog in here. If I were to overwrite any of these values, then just like in a C program, it's the final value that will be the true answer. Because this is behavioral Verilog, it's describing the function that computes what we want. It's not describing directly the hardware at all. So between begin to end, think of it like a C program. But be careful of that. We've set it up so that you can do that. In general, never think of Verilog like C. They're completely different. Anyway, our default action is to do nothing. So if we're idle, count will be 0 and next count will stay 0. That's our default action, and we don't change our data either. If we're live, and live means that we're currently sending something, and live is defined down here, and that's fine because the order doesn't matter. I'll come to that later. If we're actually sending something, then that means that our count is non-zero, and to move to the next state, we subtract 1 from count, because count tells us how many bits we have left to send, and if there's another rising edge, we have 1 less bit to send, so the next count is 1 less. And here's our shift register right here. So our shift register will start off with the number we wish to send. We actually see that in here, and I'll come to that in a second. And then every time through, so we first send bit 24, then bit 23, then bit 22. To do that, we're just going to shift our shift register 1 place to the left every time. And so you see we put a 0 coming into the rightmost bit, and this is width -2, not width -1, so we lose 1 bit on the right. So we're just shifting our data 1 bit to the left every time when we're live. How do we start? Well, if we're currently not live, but if there's a 1 on the start pin, then we want to start sending our number. So we initialize our count to the number of bits we're going to send, and that's width. If it's a 24-bit parallel to serial converter, then we want next count to be 24. And this part here is just for Quartus not to warn me that I might be truncating width. Remember, we carefully chose our counter to be wide enough to store the value of width. So I know that this is not a problem, and this is how I stop Quartus from warning me that I'm truncating it. And when we're told to start transmission, we save our input into our data register here. Finally, our output logic. Well, if we look at this one first, if count is 0, then we are idle, we're not doing anything, so live should be 0. Whereas if count is non-zero, then we have some bits to send, so live becomes a 1. And our output, well, if we're live, if we're sending some bits, then we send the most significant bit of data. And that's why we have a shift register, because first we send the most significant bit, then we're going to shift our shift register. So what was the second most significant bit will become the most significant bit. And so by just sending the most significant bit, coupled with this shifting, we end up sending each bit one after the other. If we're not live, we may as well be tidy and just send a 0 here. Although if we're not live, the receiver is going to ignore the value coming out of here anyway. Finally, we can look at the remaining module, which is straightforward. It's just the BCD to 7 segment display. And that's the same, pretty much the same as in the workshops there. It just converts a 4-bit number into the 7 individual 7 segments required to drive the 7-segment decoder. Here's our finished diagram for one more time, and we see that we're generating a number, we're putting it through a parallel to serial converter, putting it back through a serial to parallel converter, and it's driving the 7-segment displays. And when we have a look at the code working on the board, we see that everything is working correctly. The numbers being produced here are going to be displayed here.